Good afternoon, everyone. My name is Dr. Nic Scott. I'm a research astronomer here at the University of Sydney. In my research, I study nearby galaxies and how they've formed and evolved. But today I'm going to be talking to you about one of the big tools I use in my research, spectroscopy. This is a very big subject covering lots and lots of physics. We're going to touch a little bit on electromagnetism, optics, quantum mechanics, thermodynamics, and of course, plenty of astronomy as well. We only have 30 minutes, so it's going to be a lightning tour. We're going to cover the basics in the first part of this talk. The middle part of the talk is going to focus on the different kinds of spectra we're going to see coming from nature. And then finally, in the last third of this talk, we're going to focus a little more on astronomical spectra. So what kind of spectra we get from astronomical objects and how those spectra tell us about the properties of those objects. Okay, now I'm going to start off with a little whiteboard session here, just talking very basically about spectroscopy. My drawing skills are not the best. I'm an astronomer rather than an artist, so you'll have to bear with me a little bit, but hopefully everything will be clear. So in spectroscopy, what we're doing is we're taking a beam of light. Let's make this beam of light white. For now, black is going to be white. Obviously, if I was drawing in white pen on this whiteboard, you guys wouldn't be able to see that, wouldn't be very useful. So we have a beam of light coming in here. This beam of light is white, and we send it through a prism. This is my very artistic prism. As it comes through this prism, this beam of light is refracted, the light is bent, and it's bent, different colours of light are bent by different amounts. So what the prism is doing is splitting light into its component colours. So white light went in this prism, and coming out of this prism is light in a range of colours. I'm just going to draw blue and red on here for now. But in the middle we've got green light and all the different shades of light as well. This is the essence of spectroscopy, taking light and splitting it up into its different colours. Now, we're scientists, and colour is not a very precise term. Different people think red means different things. Different people argue over whether it's purple or brown or maroon or whatever. If you remember the infamous dress from a year or so ago, where no one could agree whether it was blue and black or white and gold, colour is a very subjective thing, and in science we don't like things that are subjective. So what we use instead is a more objective measure of colour, or here the wavelength of the light. So again, we have our beam of, let me just make this white again, our beam of white light coming in here. It's going into a prism down the bottom this time, and again it's getting bent. And then what we're going to want to do now is measure how much light we have at each colour or each wavelength, and then we're going to plot this on a graph. So on this side we have, on our y-axis, we have flux, just the total sort of brightness of light. On this axis we're going to have wavelength. Wavelength is very similar to, is essentially colour, but it's a more precise measurement of colour, not worrying about people arguing about what exactly red and blue means. So when we make a spectrum, we're measuring how much light we have at each colour. So down this end we might have a little bit of light, here we have a bit more, and maybe it's fading down towards this end of the spectrum. And we draw a line through all of these points. And this is a spectrum. This is a very, very simple spectrum, of course. Real spectra are much more complex and interesting, but this is illustrating the process. We take light, we split it up into its component colours, we measure how much of each colour we have, and then we plot that on what we call a spectrum. So let's just clear that now and look at some very simple properties of spectra. So again, we're going to go back to our spectrum. Here we have wavelength on the x-axis, flux on the y-axis. Flux can also be brightness or luminosity. They're essentially all different measures of how much light we have. The higher the flux, the more light there is. And another way of describing wavelength, as I said, is colour. On this axis, at low wavelengths, we measure wavelength, I should say, in length, and particularly for optical light, so blue and red and sort of the things we see with our eyes, what you might call the visual part of the spectrum, we use nanometers. The blue part of the optical spectrum ranges from about 300 nanometers down here up to approximately 800 nanometers down here. 300 nanometers corresponds to blue light. 800 nanometers corresponds to red light. So in our spectrum here, we can measure the amount of blue light. There might be a lot of blue light, sort of intermediate amounts of green and yellow light, and then a little bit of red light. So we'd have a spectrum that looks like this. Because in this spectrum we have a lot of blue light, not much red light, this object is going to be blue. Lots of blue light, not much red light makes an object red. Something that's blue doesn't just have blue light, it just has more blue light than any other colour. We could do the same thing, but imagine it for a red object, for example. So if we have not much blue light down here, a bit more in the middle, and then lots of red light up here, this is what a red object might look like in terms of spectrum. Not much blue light, lots of red light. If we had a white object has equal amounts of all light, so its spectrum would look like this. It would be perfectly flat. So something that has the same amounts of blue light and red light and green light in the middle would look white. So these are very simple cartoon spectra. Real spectra are a bit more interesting than this, and we're going to come in a minute to what exactly real spectra look like. This is the end of my little whiteboard tutorial. We've exhausted my drawing skills, I'm afraid. So now we're going to switch over to some slides I prepared earlier. So before getting on to different kinds of spectra, I just want to say exactly how we make spectra in astronomy. We don't use a prism. A prism is a very crude tool. It makes a nice little rainbow, but it's very hard to know exactly how much you're spreading the light out. They're not really very efficient. A lot of light is reflected and lost. Astronomers use something called spectrographs. These are effectively very, very high-tech, very efficient, very precise prisms. And the one you're seeing here is the spectrograph we use at the biggest telescope in Australia, the Anglo-Australian telescope. This spectrograph is called AA Omega. And the light comes in from the far back corner in this image. It comes into those arrangements of lenses and gratings you can see in the middle. And this is where the fancy version of a prism lives that splits the light up. And then it's sent to these two shiny silver objects on each side, which are the cameras. They're basically very expensive digital cameras that are very, very good at counting exactly how much light is there. Most telescopes in the world will have a spectrograph similar to this one, maybe not quite as fancy as this one and as shiny, but it's kind of a workhorse of astronomy. So many, many astronomical measurements are made using spectrographs like this one. So that's kind of an introduction to spectra in general. What kinds of spectra do we have? Well, we can very broadly divide spectra into three kinds, and you can see them summarized here. We have emission spectra, continuum spectra, and absorption spectra, and you can see these look very different. Emission spectra is composed of lots of little lines, a continuum spectra includes all the different colors, and then an absorption spectrum is a bit like a continuum spectrum with certain parts of light missing, so there are dark lines in an absorption spectrum. And these three spectra are made in different ways. So the emission spectra, our first example where we had those thin lines, is the most fundamental one. And this comes down to quantum mechanics. So we're bringing in another part of physics here to understand this. In an atom, you have a few electrons orbiting that atom. In hydrogen, you only have one atom, one electron, the example shown here. But in other atoms, you might have more electrons than that. And in atoms, electrons can only live at certain places, certain orbits, effectively, certain distances from the atom. And these correspond to very specific energies. One way I like to think of this is imagining them as shelves. So you have your wall and you have shelves at different positions on this wall, different heights above the floor. You can put an electron on the shelf, it'll sit there, or a ball, say, but you can't put it in between shelves. You can't place things at these intermediate steps. So within an atom, we have electrons sat on these different energy levels, and they can move between those different energy levels. Changing energy level results in a change of energy. If you're going up energy levels, then you must have gained energy somehow. If you're going down energy levels, then you lose energy. When you lose energy, what happens is you emit some light that carries away this energy. And then the wavelength of light corresponds exactly to the amount of energy that was lost. So that's why we get these patterns of lines. Each one of these lines corresponds to a change between one of the pair of energy levels. That pair of energy levels has a very specific energy, which corresponds to a specific wavelength of light, which then corresponds to a specific color. So we're only seeing light at these very specific wavelengths related to the energy levels, not at all different kinds of wavelengths. So these emission spectra are produced by hot, low-density gas. So you have to heat the gas up so it'll glow. That's why it needs to be hot, so it can release energy. And low density we'll come to in a second when we talk about the next kind of spectrum. As I said, the pattern of lines you get is related to the energy levels that each atom has, and different elements have different patterns of energy levels. That's determined by the number of protons and neutrons in the nucleus, the number of electrons, and the very kind of detailed quantum mechanical structure of these different elements. What this means is that every different element has its own pattern of lines as well. And there's a link on the slide here. Hopefully you'll all be able to copy this and have a look at it at a later time. But I just want to quickly switch to a web browser to show you this. This is a very nice tool I came across when I was looking for interesting links for this site. So this is a periodic table of elements. I'm sure you're all familiar with this. We've got hydrogen and helium and all the different elements. So if you go to this website and click on any one of these elements, it brings up the corresponding spectrum. So hydrogen spectrum is here. It's very simple. Only has a few lines, and that's because hydrogen only has one proton and one electron. It's just not a very complicated atom. If we pick a more complicated atom, like I think Y is ytterbium, I'm sure your chemistry teachers will be able to tell you more, or correct me if I'm wrong, you get a much, much more complicated spectrum of lines here. This is because it's a more complicated atom. It has many more protons and neutrons that are interacting in different ways, lots of electrons, a very complicated series of energy levels that produces this dense forest of lines. So of course there are many more elements here that you can look at. I think this is a fantastic little website. It's made by a chemistry professor in the US, I believe at the University of Kansas, so I take no credit for this. But in your own time, have a look at it, play around, look at the different spectra of the different elements and see how they get more complicated as you go to more complicated atoms. So switching back to our slides, that's emission spectra. Our second example spectrum was continuum spectra. And this is where you don't have those lines, but you have a complete set of colours. Now, this isn't a white spectrum. It's very important to recognise that continuum spectra can have different colours, and that's because you can, as we showed in our little whiteboard tutorial, you can get more light coming at different wavelengths. You have some of all of the different colours, but if you have more blue light than red light, then you're going to look blue. If you have more red light than blue light, then you're going to look red. If you've got something in the middle where your light is peaking, like in this example here, then you're going to look sort of greenish, greeny yellow in this case. So what's happening with continuum spectra is we take our emission spectra, and you could see that in the more complicated atoms the lines were getting denser and denser. We were never quite filling in all of the space, but we were certainly getting a lot closer to a continuum spectrum. Now imagine if you combine a few different elements, then you fill in some more of those gaps. And what happens when you make these materials very dense is that different atoms start to interact with one another, and that changes and in fact broadens the sort of spacing of energy levels within these atoms. The more and more atoms you add into your material, the bigger effect this has, until you take those individual sort of lines and you smear them out, and eventually you fill in all of the gaps. So that's when you get a continuum spectra. This only happens in dense materials, so if you have a very dense gas, lots of gas, or solids which are already extremely dense. So most solids produce continuum spectra when you heat them up. One really interesting or special example of a continuum spectra is the so-called Blackbody spectrum. This is a kind of a perfect spectrum that has none of those features due to the energy levels. It doesn't have any kind of structure at all. It's a perfectly smooth curve. But the properties of this Blackbody spectrum only depend on one thing, and that's the temperature of the thing doing the emitting. It doesn't matter what it's made of, it doesn't matter what shape it is, none of that matters. It's only the temperature of the thing doing the emitting. This is you can think of this like a Bunsen burner flame, for example. Not a Blackbody, but it's going to illustrate the sort of things we are. Or maybe a fire at home, or when you heat up a piece of metal. When that object is relatively cool, it's not that hot, then it will appear red. Most of the light it's emitting is at red wavelengths. As you heat it up, it's going to go into sort of yellowy colours and get hotter, and then as it gets really, really hot, it'll become even blue hot or white hot. So this is being illustrated in the slide here. We can see a Blackbody spectrum for 3 different objects. And then on the x-axis we have wavelength, so this is colour again, intensity, luminosity, flux are all measures of how much light we have. For our cool object, it's emitting its light closer to red wavelengths than blue wavelengths, so it's going to appear red. Then as we go to the hotter and hotter objects, the peak of their wavelength that they're emitting moves to bluer colours, and so those objects appear blue. Now, that has another link on here, and this is just going to be a little hands-on demonstration that you can try for yourselves and see how the kind of the blackbody spectrum you get for things of different temperature vary in color. So we've got a little slider here, we can change the temperature, we turn it all the way down. This is in Kelvin, so 300 Kelvin is approximately 30 degrees Celsius, so kind of everyday temperatures that we're used to, and you get very little light here. And that's good because, you know, your skin is something like 30 or 40 degrees Celsius, and your skin isn't glowing, you're not emitting light. So very low temperature things don't emit light, at least at visible wavelengths. They do emit light at near infrared wavelengths, so longer wavelengths actually, and that's how kind of night vision cameras work and that sort of thing. But as we heat up and heat up, you can start to see we're starting to produce a bit more light here. There's a little bump here, and then when we get up to sort of the temperatures of a light bulb, and you know what, I'm going to zoom in so we can see this a little bit more clearly. There we go. So now we're at temperatures of a light bulb, a few thousand degrees, and here we're producing most of our light towards the red end of the spectrum. When you look at a light bulb, it's kind of yellowy red. It's certainly not blue or white or green or any of those colours. Then as we get hotter and hotter and hotter, oops, shot up a little bit here. Now I might need to move out. The other thing I should say is when you get hotter, you produce more light in total, which is why this curve is going up as well as the peak is shifting. There we go. Let's climb again and again. Still didn't zoom out enough. Let's zoom out. Here we go. So something as hot as the sun, which is at several thousand degrees, twice as hot as our light bulb, for example. You can see that the peak here is in the green part of the spectrum, but most of the light is coming out in the yellow and red parts. So the sun, because it's emitting light at all wavelengths, appears sort of white or even slightly yellow, just because there's a bit more light in the yellow and red part of the spectrum than there is in the blue. If we go even hotter, so to different kinds of stars perhaps, or you know, something that we've heated up very, very hot, like an iron bar to tens of thousands of degrees, you can see now most of the light is being emitted at blue wavelengths. So this would appear blue. This is a very nice demonstration of a blackbody curve, and in particular, the fact that as you heat something up, it produces more light in total, which is described by the Boltzmann equation for blackbodies, and the fact that the peak wavelength, or effectively the colour of that object, is changing to bluer wavelengths as we get to higher temperatures. And that's known as Wien's law, W-I-E-N, Wien, who was a physicist in the 19th century, I believe. Okay, so our third kind of spectrum was absorption spectra. And this looked like a continuum spectrum with bits of light missing. And the great thing is, that's exactly what it is. If you imagine our emission spectra, where we had little lines in it, where something was being emitted, and that was being produced by a hot, dense gas. So what we're going to do now is take our continuum source, where we've got light at all wavelengths, and in front of that, between us and the continuum source, we're going to put some dense gas. Now we'll make this gas cold, so it doesn't emit light of its own, but we'll make it, a relatively low density gas, I apologise, that is cold. So it's not emitting light on its own, but if we did heat it up, then it would emit something like an emission spectrum. So when the light passes through this cold gas, the exact opposite process of an emission spectrum happens. In an emission spectrum, we had electrons falling from high energy levels to low energy levels and producing photons of different wavelengths corresponding to those energy gaps. What happens in an absorption spectrum is the photons that are travelling through this gas get absorbed by the gas, and that takes electrons from low energy levels up to higher energy levels. And now only photons of certain wavelengths can be absorbed, wavelengths corresponding to the right energy to get you from a lower level to a higher level. Again, so that exact same gap that we saw in the emission spectrum has to be reflected in the absorption spectrum, but here we're seeing it as missing light that's been absorbed rather than light that's been emitted. And then we just put this through our prism again, and we get our nice absorption spectrum, which is a continuum spectrum, but with specific wavelengths of light missing. So just to summarize this, we've got three different kinds of spectrum. We've got our continuum spectrum, one example of which is a black body, but there are non-black body continuum spectra, where we get light at all different colors, and that's normally produced by very dense materials, solids, or dense gases. We have our emission spectrum, our emission line spectrum, which is produced by a hot, low-density gas, where we're seeing the effect of these different energy levels, and we just see light corresponding to specific transitions between energy levels. And then finally, we have an absorption spectrum, which you can think of as a continuum spectrum minus an emission spectrum, in a sense, where we start off with a continuum spectrum, and then we put a cold, low-density gas between us and it. That gas is absorbing light at certain wavelengths corresponding to the same lines we see in the emission, and that's very well illustrated in the slide here. You can see the black gaps in our absorption spectrum. These lines here correspond exactly to our bright lines in our emission spectrum. These are the three kinds of spectra that we typically see in everyday terrestrial sources, so here on Earth, but also when we're looking out in the universe as well. So what kinds of things in astronomy produce these different sorts of spectra? Well, nothing produces a perfect black body. It's kind of a theoretical construction. You can make some certain machines that produce spectra very, very close to black bodies, but nothing is a perfect black body. There are a few things in astronomy that are very close to perfect black bodies, though. One of these, which is shown in this plot on the left, and remember, this is a plot of wavelength against flux. So on the y-axis, we're just measuring how much light there is, and then on the x-axis, we're measuring the wavelength or the color of light. Blue light is down at short wavelengths, red light is at long wavelengths. And in this example, this white dwarf, we don't have very much light at red wavelengths, and then we have a lot of light at blue wavelengths. So this object would look sort of bluish, maybe slightly yellow. White dwarfs are dead stars. They're kind of the remnants of more massive stars that have used up all of their fuel. They've stopped conducting nuclear fusion, and all they're doing is cooling down and emitting light because they're still very, very hot. This phase can last for billions of years, and they gradually get colder and colder and colder, losing energy until they get so cold they don't really radiate away much light at all, and then we can't see them anymore. But white dwarfs are still relatively hot. On the right-hand side, over here, we have the spectrum of a very hot young star, so sort of the opposite of a white dwarf. This is a star that's just been born. It's very massive, and when you have a very massive star, it has lots of fuel, and so it can burn very, very brightly. And that's what we're seeing here. Both of these spectra are somewhat similar in that they're quite smooth and featureless. Their shape is largely determined by the temperature of the thing doing the emitting. And if you look very closely at these spectra, you can see that the white dwarf, for example, is just starting to turn over on the very left-hand edge of this plot, so we're reaching the peak. Whereas our O star, our very young star, is not. This is still climbing. So just looking at these two plots, you might expect that our O or B star, our hot young star, is going to be bluer than our white dwarf, and that's exactly what we find in astronomy. So we're already learning interesting things just about these two kinds of stars. Now if we look at something a little bit more interesting, here we have the spectrum of the Sun. So on the left-hand side, we have the spectrum of the Sun as you would see it from space, so excluding the effect of the Earth's atmosphere. The black sort of wiggly line is the actual spectrum of the Sun, and the dashed line here is a black body spectrum of something as a very similar temperature to the Sun. You can see it's a pretty good match, but it's not a perfect match. So what we have with the Sun is something close to a black body, but the outer layers of the Sun's atmosphere, is absorbing some of the light. And the wavelengths it's doing the absorbing at is determined by the chemical composition and the ionization of the Sun's atmosphere. So comparing the sort of the black body spectrum to the dips we see in the spectrum of the Sun, we can learn about the chemical composition of the Sun, what atoms and elements are in the Sun. We can also learn about the temperature structure of the Sun, so where it's hot and where it cools in the outer parts. And there's a lot of information in the spectrum here about the structure of the Sun. On the right-hand side, we're seeing something similar. The black line here is now the spectrum of the Sun seen from the Earth. So this is after it's gone through the Earth's atmosphere. And comparing the left-hand side to the right-hand side, you'll see there are many, many more dips here. And this is because the elements and atoms and molecules in the Earth's atmosphere are doing a lot of absorbing as well. So they're absorbing light at specific wavelengths. And you can see on this plot that some of the particular dips are labeled with the atoms or the molecules responsible for doing the absorbing. You'll notice that water is a very common feature. So by looking at the absorption spectrum of the Sun coming through the Earth's atmosphere, we see that there's a lot of water vapor in the Earth's atmosphere, which is good for us, obviously. We need water to survive. It's bad for an astronomer because it already absorbs a lot of the light. So you wouldn't be able to study, say, whether the Sun has any water in it. It doesn't. But you wouldn't be able to study that from the Earth because the Earth's atmosphere is already absorbing all the light there. So another really interesting astronomical object is an emission nebula. So these are the most spectacular images you see coming from different space telescopes. This is a Hubble Space Telescope image of the Orion Nebula, and this is a region where very young stars are being formed. Young stars are formed out of gas. Young stars are very hot, so these young stars heat up the gas around them, and that causes the gas to glow, and so you get an emission spectrum from this low-density, very hot gas. And then in the bottom right-hand corner, we can see the emission spectrum corresponding to the Orion Nebula. By looking at all of the peaks, we can associate those with different elements. Remember, every element has its own specific sort of fingerprint or barcode of emission spectra, and then we can learn what elements are present in these very distant emission nebula that new stars are being born out of. This is an example I really like. Again, we've been looking at kind of stars being born and stars dying. This is kind of a star dying, or one of the things that happens to a star when it dies. This is the very famous Ring Nebula, a spectacular Hubble Space Telescope image down here. Lots of different colours in there. This is a planetary nebula. So this is when an old star starts to die, and it produces a strong wind that blows off the outer layers of its atmosphere. So what we're seeing here are the outer layers of this star's atmosphere that it's already blown away. This is a colour image down in the bottom right, but here we have what you might call a spectral image. So we're taking an image at different wavelengths, and that can tell us where in this nebula different elements are present. So if you look over here on the right-hand side, we've got a red blob. That corresponds to a very specific wavelength that's known as H-alpha. It's an emission line of hydrogen, and we see that hydrogen is present pretty much throughout this nebula. That's not surprising. Hydrogen is the most common element in the universe, so you expect it to be everywhere. If we go over here, though, you might see that these bluer structures are associated with oxygen, and these tend to be only in the middle of the nebula. So these heavier, more complicated elements tend to be closer to the star, so we can learn about the structure of these nebulae as well. And then finally, dear to my own heart, my own area of research is galaxies. Galaxies are very complicated things composed of stars and nebulae, even emission from supermassive black holes in their very centres, which I think you either have already heard about in this talk series or will be hearing about in the next couple of days. And galaxies have very varied spectra as well. So here are 3 examples of galaxy spectra. On the left, the biggest one, we have what's called an early type galaxy that's mostly composed of old stars, and it'll be red. You can see there's not very much light here at blue wavelengths, more light here at red wavelengths, and then we have lots of absorption features. On the top right here, we have a young galaxy that's forming lots of stars. The young stars are hot and blue, so you get more light at blue wavelengths, less light at red wavelengths, and we also get these emission lines here coming from the emission nebulae where the young stars are being born in this galaxy. And finally, this bottom right example looks a little bit like our star-forming galaxy, but this is even bluer and hotter and has very different emission lines. And this is actually light coming from an accretion disk around a supermassive black hole in the center of a very, very distant galaxy, sometimes known as an active galactic nucleus, or an AGN, or a quasar or a quasi-stellar object. So today, just let me pull the camera up so I can see you guys. To end. So today we've talked about 3 different things, or 3 main topics. What is spectroscopy? How we split the light up into different colours and measure the amount of light there is at different colours, and we can plot that on a graph that we call a spectrum. We've looked at the different kinds of spectra we get, so continuum spectra, absorption spectra, emission line spectra, what the physical mechanism is that creates those different spectra, and where we kind of expect to find them, hot gases, solids, very dense gases, cold gases, those sorts of things. And then finally we've talked about where you find these spectra, different kinds of spectra in the universe, different objects that produce the different kinds of spectra, and how we use these spectra to then study the different kinds of objects, how we learn about their chemical composition, their temperatures, and in fact we can also learn about the motions of stars as well. I haven't talked about that at all, but that's another thing we can do with spectroscopy. So Spectra is an extremely valuable tool for astronomy and in all other fields of science as well. So I've run slightly over time, I apologise. Do we have any questions from the live chat? Okay, obviously I've done a fantastic job of explaining everything. You're perfectly clear on how we use spectroscopy in astronomy and what causes different kinds of spectra and how we make spectra from our telescopes. So it's been a pleasure talking to you guys. I encourage you to explore the couple of links that I provided and look through these slides and study the different kinds of spectra you get from astronomical objects yourselves. Thank you very much.